Hi, this is AJ from Radius. I'm founder of Radius. Radius is building shared sequencing layer for rollups. Shared sequencing layer is kind of a new infrastructure in modular blockchain to help developers deploy their rollups kind of easily and also to operate them efficiently. So you might not familiar with a sequencer. A sequencer is kind of validators for Ethereum. So right now, many rollups have really centralized sequencers. So I think that a shared sequencing layer can help them decentralize to operate them better. So yeah. So sequencer has a kind of many roles, especially receive transactions from end users and aggregate them and execute them and post the results and also prove to layer 1. So if you want to build your own Rollup network, you need somehow decentralized sequencers because centralized sequencers have really a big issues like liveness and censorship and also MEV stuff as well. So decentralization is different, meaning in rollups compared to layer 1, because in layer 1 decentralization is essential because they're security, but in rollup space they need to operate them more transparently, because it's gonna decide for example how much end user in rollup is gonna pay or something. So there are two ways to decentralize sequences. First, we can take this monolithic approach by having multiple sequencers doing the same thing, the every functions that I just mentioned. But it's really difficult because there are going to be many rollups, which means that we need much more sequencers for these multiple rollups. So Radius would like to take this modular approach, which means that we are going to specialize these functions, especially like a builder's network to build block, a proposer to execute them and propose the block, and also a prover for generation proof for rollups. So this modular approach, I think will take care of this whole overload that many rollups are going to bring to the space. So, and then probably our restaking stuff can be applied for these sequences. So I will explain later. So we do really care about this MEV actually happening in layer 2 space. So Radius use encrypted mempool to prevent this bad MEV happening on user side in layer 2. I know that there is some controversial in MEV stuff but we define bad MEV, which would lead to financial losses on user side, like a front running and sandwich attack. You might lose your funds to MEV searchers. So but MEV is all about how to order transactions. So we basically use encryption to hide the contents of your transactions from these MEV searchers, so no one can see your contents. And then also, if we encrypt the whole transactions, it also help this Rollup network censorship resistance as well. So that's why we use encrypted mempool. And then also another important one is that the reason why we are going to use this Rollup network is that we can get a fast pre-confirmation from this Rollup network. If you want to finality from Ethereum, you should wait at least 12 seconds. But if you use encrypted mempool in the Rollup, you can get a really fast pre-confirmation thing saying that your transactions will be included in a specific index of next block or something. So you can get a better user experience from it. So that's why we decided to use encrypted mempool. So let me go deep into how it works. So basically we use a time lock encryption thing, which means that if you end user wants to create transitions, he needs to encrypt them. But the encryption key is from the time lock puzzle. A time lock puzzle is kind of the number of sequential computation which make this sequencer solve this time lock puzzle for a couple of seconds. So that's end user needs to generate this time lock puzzle. The solution to this time lock puzzle will be decryption key. So this solution is kept only on end user side, and then if sequencer wants to decrypt these encrypted transactions, he needs to solve this time lock puzzle. So this is where a delay comes in. So during this delay, a sequencer needs to respond to end user with the order commitment. It's kind of a pre-confirmation thing. So that's how we can get MEV resistant stuff in this with this encryption stuff. But the problem is that this sequencer cannot, since this sequencer cannot see the contents of the transitions, some malicious end user can attack against sequencers. Like some malicious end user can generate invalid encrypted transitions with like a gibberish transition and then deliver it to sequencer. Sequencer cannot distinguish if this encrypted transition is valid or not, which means that sequencer is going to waste on their computing resources to solve this time lock puzzle to find the decryption key. And also, if a sequencer included this block into a next block, it's going to waste a block space as well. So these two wasting thing would lead to network instability. So it's a really bad one. So that's why we Radius uses GKP stuff to prove that this encrypted transactions is valid without decrypting it. So so when end user creates the transactions, it also needs to generate this GK proof to prove that this whole encryption process is done correctly. So which guaranteed on sequencer side that this encrypted transactions is valid. So that's the protection for sequencer side as well. So and also I said that sequencer needs to respond to user with the order commitment. What if a sequencer break this order commitment? So how we can enforce this sequencer to keep this order commitment? So it's kind of simple. We can take a slashing mechanism here, because a sequencer publish a confirmed block to layer 1. In smart contract, layer 1 is going to store a list of transaction hashes that he has committed to so far. So, and then end user can find out this a block published on layer 1. It can find out if this order commitment is kept or broken. Or if he finds out that it's broken, he can claim to the smart contract on layer 1. So it works trustlessly because it verifies this claim in a smart contract. So there's nothing that a sequencer can do with it. So if this claim is success, this sequencer is going to be slashed. So another one is that sequencing layer is really care about the liveness. Liveness is really important for this sequencers because this whole Rollup network is kind of a scaling solution. So we take this leader-based sequencing network. So this user can send encrypted transactions and ZK proof to sequencing sets, and sequencing sets can generate this order command by this leader, and then you can make sure that consensus is also happening during among these sequencer sets. So there are multiple sequencers in this set. So we can make sure that if a leader's broken or leader stop working, another sequencer can take over. So in our system, we randomly selected these sequencer sets from the bigger sets. So right now we are using a VRF, verifiable random function, to make sure that this sequencer set is selected randomly. So in this case also, restaking stuff can be used, because it's really difficult to set up new sequencer sets from out of nowhere, but there's validated sets already staked on Ethereum, and then restaking would be help this set up a good quality of sequencer sets. So another one that sequencing layer can help this Rollup network is that interoperability. Many people criticize this Rollup-centric approach, is that because there will be fragmentation happening between multiple rollups. But I think that sequencing layer is really well positioned to solve this interoperability between rollups, because this sequencer set have a full control of building a block for multiple rollups. So, for example, flash loans, it has multiple transactions that should go to multiple rollups. When sequencer received flash loans transactions, it can make sure that each transaction in flash loan transaction will go to directly included in block for each rollups. So, which means that this sequencer layer can guarantee this atomic inclusion. But problem is with this atomic inclusion that even though we make sure these all transactions are included each rollup, we cannot guarantee these transactions are gonna be not reverted. It can be reverted somehow. So that's where atomic execution comes in. So now, as I said before, order commitment, pre-confirmation, can enforce this sequencer to keep this order commitment, because there will be a slashing condition happening if he doesn't. So this order commitment, order validation concepts can make sure that this atomic inclusion leads to atomic execution. But it's really a difficult one, because we are still researching it, if it works or not. So, but in quite near future, we can publish if it works or not. So anyway, and then also this sequencing layer track all the states of this interacting rollups. It can also it tracks all the states of cross rollup, like a flash loan transactions. When this atomic execution is failed, this sequencing layer can point out the exact point where each rollup should roll back. So that's how the security also makes sure with this sequencing layer concept. So yeah, probably this is my last page. So we all know that there will be many rollups comes in. Probably tsunami of rollups will happening in this space, which means that we need really many sequencer sets for this. Make sure these all rollups entering Ethereum can be realized. So with this modular approach and also restaking stuff, we can make sure this we can support these millions of rollups better than without them. Okay, that's the end of my talk. Thank you very much.